Alright, so today we are going to continue our discussion on the SRAM's basic operation. So far we talked about the read operation, so today we are going to talk about the write operation. So here for the write operation, let's assume the N1 node store 0, and then N2 node store 1. And here the write operation tends to flip the N1 node from 0 to 1, and then the N2 node from 1 to 0. So what you need to do is to prepare the data pattern you want to write from the external data bus to the bitline and bitline bar. So in this case, since you want to write 1 to N1, so then the bitline will be biased at VDD. And then bitline bar will be biased at 0. Then you turn on the word line, cascades down. Then the write operation will start. But if you look at the left branch circuit here, you see that this cascade 1 is turned on, and because here you have the VDD, and then here this is also VDD, and then this is ground. So you will have the current flow like this. So the N1 node voltage will increase a little bit. But if you look at this circuit, it actually is the same as the read operation, as we discussed earlier here. If you look at the left branch of the read operation versus the write operation, they are exactly the same. So in other words, so here the N1 node will increase a little bit, but the N1 node will not flip, because by the read operation, we define the beta ratio. So here this N1 node is designed not to change to ensure the correct read operation. So the N1 node will not by itself flip from 0 to 1. So this is the same as a read operation. So this 0 to 1 should not happen. Then what triggers the write operation? We have to look at the right branch of the circuit here. So on the right branch, the bitline bar is grounded, and then here the cascade 2 is turned on. Here this is stored. This stores like VDD. So this is the VDD. So then we will have the current flow, the cascade 2. And this current actually comes from the power supply through the pull up to PU2. You have this green current path from the VDD to the bitline bar. And this current path actually also forms this voltage divider between PU2 and PG2. So the N2 node voltage will decrease. So this VDD will decay. If the design makes the N2 node voltage decay to certain low voltage level, then let's say if the N2 decays to close to 0, then what will happen is that here this N2, remember this is also the input to the PU1 through here. So this N2 voltage, if it's low enough, then the PU1 will be turned on. PU1 is a PMOS transistor. The PMOS transistor, you know, the VGS, this is G, this is S for the PMOS. So if this VGS is negative, sufficiently negative, then the PU1 will be turned on. That means you will have additional current flow from the PU1 to the N1 node. So you got additional current to charge up the N1. Then N1 voltage will further increase. As we just mentioned, by this PG1 current itself, the N1 node voltage will not increase too much, but now you get additional current from the PU1. Then the N1 voltage will further increase, and eventually N1 will flip from 0 to 1. Of course, N2 flip from 1 to 0. So this is how the write operation occurs. So to summarize here, the write operation is initiated from the 1 to 0 transition. In this example, that's the write branch. So first, this one node needs to be decayed to a certain low voltage. And then the 0 to 1 will follow, basically. So you have basically two phases in the write operation. Remember, 1 to 0 happens first, and then 0 to 1. Why is that? Because 0 to 1, by design, do not flip the data. This is the same as the read operation, as we mentioned earlier. So any questions here? Or if you want to write the same data pattern, then nothing will happen. That's already the data you stored. Nothing will happen. So this is to flip the data. All right, so let's look at the timing diagram here. So as we discussed, you need to prepare the data pattern from external data bus to the BL and BL bar. So in this case, we want to have N1 to be 1. So BL will be biased at VDD, and BL bar will be biased to ground. So this is the data pattern you want to store. And then you turn on the word line. So the N1 and N2 voltage will change. So here you look at this waveform. You will notice that the N2 start decay first before the N1 rise up. So only when N2 is low enough somewhere here, the N1 will rise up. So in other words, this cross point should be somewhere close to the ground, definitely below the half VDD. So the N2 starts decaying first before N1 rise up. And then eventually you will flip the pattern. So N1 will become VDD, N2 will become 0, ground. And then after that, you can close the word line. And then after that, typically we will enable the pre-charge signal to pre-charge both bitline and bitline bar to be VDD, because the next operation may be the read operation. So always the standby mode is to have the bitline and bitline bar both pre-charged to VDD. So here for the write operation, the first phase, as we discussed, in this example, you will focus on PU2 and PG2, those two transistors, because this initiates the write operation. So if you only look at those two transistors here, so again, you can use resistor to approximate those two transistors. Right, so here you have the PU2 channel resistance, and then the PG2 channel resistance. So you have this red current path. And again, the condition we mentioned earlier, the N2 node voltage needs to be low enough to trigger PU1 additional current. So then here the requirement is this N2 node voltage needs to be pulled down sufficiently low. Then if you use the resistor voltage divider, then you know the condition. PG2 and PU2, let's say the resistance, the PG2 should be larger or smaller than PU2, larger or smaller. smaller, right? So you want the PG2 to be close to ground. I mean, the voltage drop across PG2 to be small. So in other words, the transistor, let's say, in terms of the conductance, then PG2 should be stronger than PU2. And we know the conductance is related to the current drivability, and current is proportional to W over L. And then here we can define the gamma ratio. This is different from the beta ratio. So the gamma ratio is defined as the W over L of the pull-up transistor divided by W over L plus gate. And this one should be smaller or equal than 1. You want the cascade to be stronger up. And then my question here is, if you have the same W over L, say for the pull up and cascade, they have the same W over L, does this condition be satisfied? If you have the same W over L, is this valid equation? Yes or no? No? Yes? It's yes, right? Why is that? Because the NMOS and PMOS, normally NMOS is stronger because the mobility of electron is larger than that of hole. So even you have the same W over L, then typically this condition is satisfied because the NMOS is used for the cascade and PMOS is used for the pull up. So you can use the same W over L. All right, so let's have a comparison between the read and the write. So the read, we care about the PG1 and PD1 because here we want the N1 node to not disturb. So here the N1 node voltage increase should be minimized. And then you want the PD1 to be stronger than PG1. So you can pin the voltage of N1 closer to ground. And then the write operation, since this part is protected, so what you need to do is to look at the PU2 and PG2. In this case, you want N2 node voltage to be as small as possible because you want flip from 1 to 0. Then the PG2 should be stronger than PU2. So any questions here? Look at there's questions from online. No? All right. Okay, so let's have a big picture of the whole array. So this is a diagram for the SRAM array and its peripheral circuits. So the array is organized into the rows and columns, as we discussed earlier. And no matter what memory technologies you are talking about, then you always have the word line rows and bit line columns. So for the SRAM, we have the 2 bit lines per cell. One is bit line and then the other one is bit line bar. And then we will have the pre-charge circuit. This is to pre-charge both bit line and bit line bar to be VDD because you want to prepare for the read operation. And then we should have the column marks. This is to select which column you want to read or write. And the column marks controlled by the column decoder. Didn't draw this out, but you should have a column decoder. And then after the column marks, then you will choose either sense amplifier for the read, and then or the write amplifier for the write. And then the sense amplifier, the output will be latched in a flip-flop. And then you have the external data bus. And if we draw the transistor level schematic, this is what you may see on the column side. The columns peripheral circuits. So here, this is a memory cell. For example, your 6-transistor SRAM. And then here we have this pre-charged circuit. And pre-charged circuit is also called equalizer. So you have 3 transistors like this. So the 3 transistors are controlled by the same enable signal. So here you will have a pre-charge enable signal to control those 3 transistors. So those are 3 PMOS, and then this will be basically attached to VDD. So if you enable this VDD, the bitline and the bitline bar will be biased to be VDD simultaneously, because here the middle, this cascade transistor needs to balance the source and the drain voltage, and eventually once you reach the equilibrium state, steady state, no current flow from bitline or bitline bar. That means both bitline and bitline bar reach VDD. So those 3 transistors help you to equalize the voltage between bitline and bitline bar with VDD. And then we have this mux. This mux is a codon selection mux. So mux, this is like a transmission gate. And then basically you select either the read path or the write path. So here you have the read path in this like dash box. Then the write amplifier is on the right. So this is just to select which one to go through. And then for the sense amplifier here, again, we have this pre-charge equalizer circuit. This is again to balance those 2 voltage. Because for the read operation, we need to have both bitline and bitline bar with VDD. So you want to ensure that this is also VDD to start with. And then the core of the sense amplifier is shown here. This is so-called the latch-based sense amplifier. So essentially here you see this is a cross-coupled inverter here. This inverter is gated, blocked by sense amp enable signal. So here you have a NMOS transistor to connect this latch to ground. But before the sense amp enable, then basically here this is disconnected. So this latch in the middle is in the floating state, because here there's no path to the ground. Therefore, the latch here is floating. Since they are floating, then you can have both those 2 loads be VDD. Because here this is disconnected to the ground. Now the read operation first, as we discussed, then the bitline, for example, if you store 0 here, store 1 here, then the bitline will see a decay. So it will have the VDD minus delta V, and other side bitline bar will be VDD. So you have a voltage difference between those 2 loads down to here. Once you create this voltage difference, or let's say the sense margin, delta V, then you will enable the sense amp by this sense amp enable signal. That means you will have a path to the ground. So then this latch will be functional. And then here latch, will always have 2 stable points. Since the left-hand side is smaller than the right-hand side, so the left-hand side will be flipped to 0, and the right-hand side will be staying at 1. So this is how the data is read out. And then you have this flip-flop, so you will latch those 2 data to this one, and then you have a single-ended output. This will be the same as the data in 1 node. This is on the read side. So for the write operation, what you will do is to prepare the data you want to write on this D in. And then this will be simple. So you have basically a driver. This is based on inverter. And then the signal you want to write. For example, you have VDD here, 1, and then this will become 0, and then you have 2 inverters, so this will become 1. So basically, you prepare this complementary data pattern to be the bitline and bitline bar signal. Then you will write the data in, as we discussed earlier. So any questions? Peripheral circuits? Again, this is the circuit, and on the right-hand side, we show the waveform timing for the read and write operation. I will not go into the details. This is already been discussed earlier. So I just want to highlight that. So here, this you see this voltage increase. So let's say this is N1, N2. Let's use the same notation. N1 and N2. So the N1 voltage increase is minimized in the read operations. And then you create this delta V. Once you create the delta V, then you will enable the SenSamp. This one, SenSamp enable. Then you will read out this delta V. And then here for the write operation, then as we discussed, the N2 will decay first, and the N1 will rise later. And then you flip the data pattern. So this is the same as the previous timing, but here we have more signal that controls the peripheral circuits. All right, any questions? Okay, so we have one question from the chat. Can you please repeat how the voltage is going to drop in one of the nodes, the sense amplifier, when sense amp enable is high? Okay, so this is like a latch, right? So the latch will eventually have only 2 stable points. So you have a latch, something like this. So basically, this is enabled by connecting this one to ground. Before that, then this is floating, so you can have both nodes with VDD. That is fine. But once you enable it, then this voltage difference will be amplified. We can use the butterfly curve as we discussed earlier, right? So after a few iterations, then in this case, the left-hand side, this voltage will decay to ground, and this one will stay at VDD. You can use the butterfly curve to analyze that. So like one voltage is, let's say initially this is somewhere here, but as long as actually initially is somewhere here, so both are at VDD. So both nodes are at VDD. But if one of the nodes, let's say, voltage decay by a delta V, then you go through the iterations as we did for the butterfly curve earlier. Then you end up with one of the stable points. And a simple rule here is that the smaller one will go to ground, and then the higher potential one will stay at VDD. So I will not go through those iterations. You can do it by yourself. This is the basic property of the latch. Okay. So here, we will have more discussions on the SRAM stability. This is to talk about the noise margin. So the stability is quantified as the maximum noise tolerance without flipping the data. And we can have the static analysis first, and then we talk about dynamic analysis. So the static analysis assumes the noise to last forever. This is, of course, a worst case condition. It's not in practice, but it's easier to get started. So let's look at the static operations first. And then here we will consider the read and hold operation. And first we will use the butterfly curve, and then we will introduce another method called Uncurve. So the static noise margin, SNM, and this is what we have seen before. You have a latch in the middle. This is in the hold operation. So you will have those two cross-coupled latch. And then we have introduced the butterfly curve. And then for the red inverter, you have the red curve here. For the blue inverter, you have the blue curve here. 3 stable points. And then the point C is metastable, and any noise will flip it to either B or A. So here we can define the static noise margin. So the noise can be modeled as a voltage source to the V1 and V2 load. Those two load voltage, we can attach a voltage bias like V1 and V2 to N1 and N2. This is like a noise source. Since this is static analysis, can assume it's a DC bias there. So what it does is to shift the voltage transfer curve. For example, if you have V1 attached to N1, then the Vn1, this voltage will be increased by this V1. So basically you will shift the red curve towards the right. And similarly, the V2 will shift the blue curve down. And eventually, if this voltage is not enough, V1 or V2, then you will only have one stable point. So here, you will only have one stable point here. Previously, you may have the point B here. But if the noise is not enough, here you will only have one intersection. That means the data will be flipped this point A. In this example, it means V1 is VDD, V2 is 0. So that means the noise flips the data pattern if it stores the other pattern initially. So here we can define this noise margin as the square that you can fit into this two butterfly curve. So here we can define a square, and actually it's the largest, by definition, it's the largest square that's nested into those two curves. And then the static noise margin is defined as the length of the side. So that means here, this is defined as the static noise margin, the hold operation. So how do you calculate the SNM? So you may have this kind of homework, okay? So what you can do is to basically rotate the X and Y axis by 45 degrees. And if you do that, so like this red and blue curve, right? So if you do that and then look at the difference, you can look at the difference between those two curves and plot the difference here. This is the difference along this 45-degree line. So you plot this difference, and then you find the maximum here. And then, of course, you need to divide by square root of 2. Then you will get the lowest margin, because SNM is defined as here. All right, so this is the static noise margin for the hold operation. And we can also define the static noise margin for the read operation. But the read will be a little bit different from the hold. What is that? So this, again, this is the hold scenario. So the pass gate are turned off. And by the way, so here we may have those two static noise margins from this upper square or this lower square. If the transistors are matched, that means they are perfectly the same. Then you have two identical squares. But if there's process variation, then you may end up with one larger square and one smaller square. Then by definition, the static noise margin will be the smaller one. That's the worst case. So if you have a smaller square, then you have to use a smaller one. Okay, so let's look at the read operation. So the read operation will be a little bit different because here in the read operation, we have this current pass through the pass gate PG1, and the N1 voltage is going to be increased a little bit, as we discussed earlier. So for the read noise margin, you need to consider 3 transistors instead of 2. So what you need to do here to get this read butterfly curve, you need to consider 3 transistors like this. Let's draw this way. For example, this is your N1 node, and this is your N2 node. This is your BL. So you need to consider the 3 transistors like this to get one curve. So here, those 3 transistors, you see the bias, this is turned on for the read line. And then we will assume the BL is also biased to be VDD. This is pre-charged to be VDD. And of course, in the real operation, it will decay a little bit by this delta V. But since we are doing the static analysis, then we'll assume that BL will be biased at VDD. So basically, you have those 3 VDD on this circuit. Then the read butterfly curve will be a relationship between the voltage Vn1 and voltage Vn2. So what you will do is to sweep the voltage. For example, in this case, you can sweep the voltage N2 from 0 to 1. And then you look at how N1 change. N1 will change from 1 to a certain low level. This will be non-zero. Will be some voltage, let's say the voltage L, VL, some low voltage, but it won't be 0. Why? This will be because this is the voltage increase that we discussed earlier for the N1 node. So the N1 node won't be 0 because you have the current through the PG1 and PD1. So N1 voltage is raised up a little bit. So you will get a VL voltage. So if you look at that, then as you change the butterfly curve, you will get a low Vn1 voltage. So here I think this circuit corresponds to the blue curve here. So as you sweep the Vn2 from 0 to 1, and then Vn1 will decay from this 1, follow the blue curve to a certain node level. This node level is this VL. So it's not 0. V1 is not 0. It's some voltage close to 0. So this VL is eventually determined by that beta ratio, the pull down versus the pass gate conductance. So similarly, you can rotate this by, let's say, mirror this along 45 degrees to look at the other 3 transistors. Then you will end up with a red curve. And again, then this becomes a kind of butterfly. But you will notice that the square now you can fit between those 2 nested curves will be smaller. So this square is smaller than the hold operation. So that means the reed is more vulnerable to the noise in the hold. So normally when we talk about the static noise margin, if we don't specify that, we mean the reed static noise margin, because that's a more dangerous scenario thereabouts. Or in other words, you can think that during the read, the N1 is disturbed a little bit. N1 voltage increased a little bit. So it's more likely, or it's easier for the N1 node to be flipped by the noise. So that's why in the read operation, the noise margin is smaller than the hold operation. Because in the read, N1 is already kind of disturbed. Okay, so any questions here? So this is the same as what we described. I will keep that. So this read SNM smaller than the hold SNM because no level is raised up by the cascade. So what affects the noise margin, static noise margin? If you think about the parameters as a circuit designer, you will, of course, consider the power supply voltage VDD. If this VDD is smaller, then the static noise margin, or this square, will be smaller because your headroom, I mean, the maximum voltage is lower by the VDD, then this square will be lower. So that's why it's difficult to design the low voltage or low power SRAM, because you have to consider for the noise margin. And then here you want this transition to be sharp to enlarge the static noise margin. If this transition is something like this, then you know your square is smaller. So this transition depends on a few factors. The first one, the beta ratio will help. If you have a larger beta ratio, that means the pull down is stronger. Then you can pull down the voltage more rapidly. Then you can have a larger slope. And also the transistors, I would say the transistor saturation current. If the saturation current no longer saturate, if no saturation, let's say no saturation, then you will end up with this gradual slope. And then here the low level, this low level of the voltage, again, is determined by the beta ratio. So the beta ratio is very important to determine the shape of the butterfly curve during the read operation. And eventually, it will determine the static noise margin for the read. So here, we show one example how the VDD and the beta ratio affects the static noise margin. So this is a simulation. I asked one of my PhD students to perform the simulation using a TSMC 28 nanometer PDK on the 6 transistor SRAM cell. So this is simulated by the SPICE, and we of course extract the SNM using the butterfly curve. So first we simulate the butterfly curve, and then we extract static noise margin. So here, as you can see, that as we decrease the power supply from 1 volt to 0.5 volts, then your static noise margin decrease. So here at 0.5 volts, we only have like 100 or 140 millivolts in the noise margin. So this is in the nominal case, that means without any process variation. But if you think of process variation, this is very small already. And then also here, if you want to increase the noise margin, you can increase beta ratio from 2 to 3. So you can see that the noise margin can be boosted by about like 30 or 40 millivolts. Of course, this is at the expense of larger area. The transistor size of the go down. NMOS increases. And then we can briefly talk about the right static noise margin. This one is not widely used, so we can still define this noise margin for the right operation. For the right operation, then here I think in this example we change the data pattern from the previous example. So here the N2 is going to change from 0 to 1, and N1 is going to change from 1 to 0. So it's just a different example than the previous one. But no matter what, here in this example, the right branch is next to the read operation. The right branch is next to the read operation. So this N2 is similarly as the N1 in the previous example. So my point is that the right branch, you will have similar like this butterfly curve, one of the branch, similar as the read condition. So this is the low voltage of this node, read condition. For the other branch, in this case, it's 1 to 0 transition. This is what we care about for the right operation, because as we discussed earlier, right operation is initiated from 1 to 0 transition. So in this case, if you want to simulate this butterfly curve branch for the right, then you will have the bias condition like the VDD here, and then VDD to the pass gate, and then the beta here will be ground. And then again, you sweep the N2 from 0 to 1, and then you look at how N1 change. So you will have this one. If you do that, you have this curve. So this curve, first of all, if you look at those two curves here, you will only have one intersection. Why is that? Because this is the right operation. You want to deterministically write your data to be this one. In this example, it's V1 equals to 0, V2 equals to 1. So this is the data pattern you want to write. So you want to have only one intersection. And then the second one is this voltage. This voltage actually is determined by the gamma ratio. Because this voltage is a voltage divider effect between the pull up and the pass gate. So you want this voltage to be as low as possible, as we discussed earlier. So then this voltage in this example is about 0.2. So this is due to the divider effect from the PU and PG. And then the right static noise margin is defined as the square between those two curves. In this case, is the smallest square that can be fit between those two curves. So for example, it's somewhere here. And then this is your right static noise margin. Why do we want to define the right static noise margin like this? Because if you have any noise, then you will shift the curve, right? You will shift the curve. If the curve is shifted towards this side, and this curve, if you shift to the other side, then you may have some other intersection. That means your right is no longer deterministic. That's why this is defined as the right static noise margin. So you want those two curves to be separate as much as possible. Therefore, you only have one intersection here. So any questions? One question here, the largest window is going to be always the diagonal that is vertical to the 45-degree rotated axis. Will be diagonal 45 degree, yes. And then you look at, when you rotate that, then you look at what is the largest distance in the rotated axis. That's right. And then for path gate, seems like from right aspect, PG should be made stronger to improve writability, but from read margin aspect should be made weaker than increasing that. Would you see a conflict? Yes, that's a conflict. So we will actually about that in a minute. So that is a fundamental conflict, as you point out. So we will talk about that maybe after the Uncurve. Just hold few slides. I will talk about that point. Okay, so then let's introduce another method called Uncurve. So this Uncurve is compatible using the inline tester. Let's say in the testing facility, if you want to examine the yield of the wafer made of the SRAM, and then you can only probing one. You can rely on the probing of only one internal node to get the noise margin. So this is because the butterfly curve is not straightforward in the testing. As we discussed the procedure earlier, you have to simulate the butterfly curve. That means you have to probe two nodes and then monitor the change of the other node. And then after that, you get the butterfly curve, and then you need to do the post processing. I rotate the axis. And after a few steps, then finally you can get this butterfly curve noise margin. So it's not straightforward. And here we are going to introduce a more straightforward way to look at the static noise margin. So here, this is the idea. So the idea is to have a current source inject to the storage node that stores the 0 data. So here you have a current source. You have a voltage source, actually. You have a voltage source. So what you will do is to change the bias to this node and then measure the current through the voltage source. So you will get the relationship between the voltage source and then the current flowing through the voltage source. So here we can look at this curve. Okay. So if the voltage source is 0, here, then you will have a negative current flow into the voltage source, because this is the current that's flowing through the pass gate. But as long as you increase the voltage of this node, then you will gradually decrease the current, because the voltage potential between the source and drain of the pass gate will decrease, so the current will rise. And then if this voltage become too high, then basically you need to inject the current to here, and then the total current will sink towards the PD pull-down transistor. And then at a certain point, if this voltage becomes too high, then you will trigger the flip of the inverter on the other side. This is like you inject the noise, or let's say this 0. If you think this is N1 node, as we discussed earlier, then N1 node voltage increase too much. Therefore, you will trigger the flipping. After you trigger the flipping, you will have snapback of the curve. So as you sweep the voltage from 0 to VDD, then if you measure the current, you will get this kind of N shape. So this is called the Uncurve. So here are more locations for those key points in the Uncurve. So here the point B, this one, is determined by the beta ratio. And then the point P, that's the peak. This is the flipping point. And then this is the maximum voltage. That the N1 node can sustain before it flip. So here we can define the lowest margin as this distance. Use this point B will be the voltage, will be the nominal voltage increase this node, if you think this N1 node. So this is determined by the beta ratio. This is determined by the beta ratio. But if you have additional noise on top of this voltage, let's say if you increase the voltage to here, then you will go through this snapback. That means the data will be flipped. This is not what you want. So that's the maximum voltage you can tolerate for the noise. Point B is the nominal, should be there. If you have additional voltage, then it may flip. And also, here this is if you think about the current, this is the maximum current you can inject to the N1 node before it flip. So here we can define the noise margin for the voltage and current simultaneously. And here are more details. I don't want to go into those. It will be a little bit complicated. But if you really want to analyze this, you can draw the trajectory of those 3 transistors during this voltage sweep from 0 to VDD by this voltage source. So those 3 transistors pull up is a PMOS, and pull down cascade to NMOS. So here, as you go from the 0 to VDD, then you go through the A, B, T, C, D points. So the transistor's current will follow the same trajectory. So for the pull up, initially no current, and then once you trigger the flipping, then you will have the PMOS current to follow this A, B. And then for the pull down, you have this A, B, C, D like this, and for the pass gate, A, B, C, D. So all the currents, when you add up on the same plot, you will have all the current add up to the same plot. So from the Kirchhoff law point of view, right? So you have 3 currents through those 3 transistors. course, you need to define the polarity of that. If you think all of them are pointing to this node, and then some of them will be negative, right? Some of them will be negative. So then, but eventually the net current after those three transistors, if you still have net current, that net current must go through the voltage source. And this is what you measured from the voltage source. So this is like the black curve here. This black curve is a net sum of those three transistors current. So if you do that, you will have the black curve following this one. So this is a little bit complicated. I will not go into the details. But if you want to correlate butterfly curve and Uncurve, so here you will, if you plot the trajectory on the same like V1 and V2 plot, so this is the normal butterfly curve, and then this is the Uncurve. Uncurve is the relationship between the voltage V in, this node voltage, and the current flowing through this voltage source. So you draw it on the right hand side. This one. So you will see that actually from the Uncurve, this noise margin is a little bit larger than what you defined from the butterfly curve. But the Uncurve, the good news is that it determines a current margin, that is this one. So those are correlated, like those flipping points. So this is like those points are correlated between those, like those tripping points are correlated in those two methods. But the definition is a little bit different. So you get a little bit different margin. Okay, to summarize, both are static curves. For the butterfly curve, so here, those three currents from those three transistors to this node will always be zero. This is always true. So here, the static noise margin is defined as noise between two storage nodes. So this is more relevant to the transistor mismatch, VTH mismatch. And the Uncurve, this assumption does not hold. Because Uncurve, you inject the current from, you can have current injection or extraction from this node. So here is more like a relationship between the noise, between this node voltage to ground, because your reference is always this ground to the voltage source. So this is more relevant for the current injection, noise current injection for the Uncurve. So which one is better? So fundamentally, they are equivalent, as we discussed earlier. So those tripping points are actually correlated. But the butterfly curve is less straightforward to extract, because as we discussed earlier, we have to get two curves and then rotate the axis. And Uncurve is more suitable for the inline testing. Inline testing means you have wafer and you plot the array, and you can directly measure the margin for the current and voltage. So this is easier in practice. So any questions? So this Uncurve, I think, is a bit more difficult, but if you want to know more details, you can read this reference from this paper, JSSC 16. Okay, so then let's look at if there's any questions online. Okay, so let's look at some of the real butterfly curve measured from the real chip. So this is from 65 nanometer, and this was published in ADM 2004. So you see this is what we really measured from the SRAM on that wafer. So the nominal VDD is about 1.2 volts at that time, and then for the butterfly curve, as we discussed earlier, if without any specification here, is always the rate condition. So here you see this is very gradual, actually, transition, and also the low level here is raised up. So if you do the butterfly curve and then extract the SNM, you see that with the VDD from like 0.8 volt to 1.2 volt, the noise margin is about like 200 millivolt to 300 millivolts, and this is reasonable. And then this is 45 nanometer, and you can have the butterfly curve like this. And of course, you can change the VDD. And then this is 32 nanometer, and this is already like high-k metal gate. This is a paper from ADM 2008. And then if the voltage is like 0.8 volt, the noise margin is about 200 millivolts. And then in this paper, it also shows the Uncurve, the measured Uncurve with different VDD. And then this is 22 nanometer, and then here you see the noise margin from like 200 millivolts with 0.9 volts VDD. But if you shrink the VDD to 0.7 volts, then the noise margin reduced to 148 millivolts. And then this is newer data for 16 nanometer process. I believe this is from TSMC. Okay. And then here, this is FinFET technology already. And you see the butterfly curve. And then here we show a group of curves. This is to consider the variations. So you measure multiple cells, and then you plot them together. The single curve will become a band. This is due to the process variation. So this is the 16 nanometer, and then this is 10 nanometer. So 10 nanometer, you see here, this margin is pretty small already, like around like 100 millivolts, so like 0.6 volts VDD. And then this is even smaller technology node, 7 nanometer. This is from ADM 10. And you see the margin is smaller and smaller. And this is the latest technology, 5 nanometer from TSMC. This is very recent, ADM 2019. And you see the butterfly curve. Probably this is less than like 100 millivolts. So if you plot everything together like this, you will see the scaling will impact the noise margin. First of all, the power supply VDD is decreasing. Then the margin will decrease accordingly. So then this is really a challenge for the VDD plan of the SRAM today. The nominal VDD today for 5 nanometer process is 0.7 volts, 1.65 volts. So it will be very challenging to maintain the noise margin for the SRAM cell. And then there are many approaches proposed to increase the stability. And here we can have two categories of approach. The first one is to modify the supply voltage. So we are going to play with the biasing, the waveform or the pulsing scheme. And second approach is to add more transistors to the SRAM cell. We used to have 6 transistor SRAM, and you can have 7 transistor, 8 transistor, even 10 transistor. So here are the representative papers, pulsing schemes, the additional bit cell design, and you will have some homework to read some of those papers. But let's have a quick look at some of those approaches. Of course, those approaches will come with some additional overhead, either the more complicated peripheral circuits to provide the waveform you wish, or the cell size in terms of area will increase because you add more transistors to the bit cell. So the first one is the dual VDD. Dual VDD is to have different power supply voltage for the VDD to the latch in the middle, or the whirlwind pulse voltage amplitude. So for the read operation, what you want is to lower down the power supply for the whirlwind voltage lower than the nominal VDD. Why is that? Because in the read operation, if you recall, the N1 node, right? So it's you have this current flow, and then you want PD1 to be stronger than PG1. So one way to weaken the PG1 is to reduce PG1's gate voltage. So then you will have less current flowing through the PG1. Then the N1 node will be more safe. So here we show some of those noise margin. If you enable this lower down by 100 millivolts of the power supply for the whirlwind, then you can increase the static noise margin by about 50 millivolts. Of course, then if you lower too much the whirlwind voltage, then what might be the trade-off here? Any idea? If you lower down the whirlwind voltage too much, any idea? The rate speed will be sacrificed. The rate speed will be longer, right? Because the current flowing PG1 determines the rate speed. And then for the write operation, what you can do is to have a negative bitline pulse. Because the write operation, in this case, in this example, I think we flip the N1 and N2. So this is used to be your N2 in previous examples. So basically, you want to flip the 1 to 0. And as we discussed, for those 2 transistors, right, you want PG1 to be stronger than PU1. So one way to make PG1 stronger is to bias the bitline to be negative. Right? Then therefore the VGS of the, if this is negative, smaller than 0, then the VGS of the PG1 is larger, so PG1 becomes stronger in terms of a current favorability. So it's easier to pull down the N1 node to a lower level, so you can increase the write favorability. So the write margin can be boosted with the negative DL as shown here. And then here there's a read modify write operation. I will not discuss this in much details because this is one of your homework. So you are going to read this paper and then figure out what is this read modify write. So a few simple words. This is to resolve the conflict between selected column and unselected column during the write operation. So in the SRAM array, maybe the array is large, like maybe 128 columns, but the data pattern, you want to, every time from the I/O, you only have 8 bits, for example. You need to choose 8 bits out of 128 bits to write. And then you will have 8 selected columns, and then another like 100 unselected columns. So you will have some conflict between the selected column and unselected column. For the selected column, you want to have the write to be successful. But for the unselected columns, you do not want to disturb the data there. But since the selected column and unselected column share the same word line, then the word line pulse width has a conflict. For the selected word line, or selected column, you want the word line to be long enough to ensure the write is successful. For the unselected column, then the word line pulse is like a read condition there. Then you don't want the word line pulse to be too long. Otherwise, you may flip the data for the unselected column. So this read modify write is a scheme to resolve this conflict. I will leave this as your homework. And a few more words on the AT-SRAM cell. So this is another approach to resolve the conflict between the read and the write. So the idea is to write 2 additional transistors here for the read path. So the write operation is the same as before on this 6 transistor cell. But the read will be a separate path. So you have additional read word line, RWL, and then additional read bit line, RBL. So here the two passgate transistor you have here, they are in series. So one of them is connected to your storage node, like your N1 node, and the other one is enabled by the read word line. So here the RBL will be precharged to be VDD. So here when you store 1 in the N1 node, so this will be VDD. And now you enable the RWL, you have VDD. So you have the current flow to discharge the RBL by delta V. But if the N1 stores 0, then this NMOS is turned off. So you don't have the current flow. Then the RBL will stay at VDD. So here this passgate transistor state is controlled by your data pattern. So you can read out using those 2 transistors here. So you have a separate read and write. Write is still through the conventional bit line and bit line bar here. The read is additional path. So you can resolve the conflict between the read and the write. So we have this conflict between read and write, as you pointed out. I don't think we have time to go to that today. But basically, I'd like to briefly touch upon that point. So if you think about the SRAM, you have this conflict. Fundamentally, why is that? If you think about that, why is there's a fundamental problem here? So this is because during the read, you have the current flowing through the passgate. As the read, you don't want to change the data. So you want the disturb from the outside to be as small as possible. But for the write operation, then you want to write the data. You want the external data pattern to be written into the bit cell. So you want the current flowing through the passgate to be strong to change the data. So fundamentally, you have the conflict because you share the same passgate for the read or for the write. So you cannot resolve that fundamentally. So for the read operation, you actually want the cell to be stable. That means this cell is isolated from external, so it will be stable. For the write, you want the cell to be strongly coupled with the outside, so you can change the data. So that's why you have this conflict. So the AT-SRAM cell can solve this issue because now the read and write paths are decoupled. And I believe this is also your homework. You are going to read this paper and answer some questions. figure out the details of the ATSRAM itself. Alright, so let me see if there are any questions online before we end. No? Okay,